All right, so hello again. Take a moment to check that the audio is working, and I'll pop out the chat. 1, 2, 3, 4, 5, 6. It's taking a while. 3, 4, 5, 6. There it goes. Okay, it's working now. So here we are. This is going to be number 1201 on LeetCode, ugly number 3. And let's go ahead and let's get it going. So yeah, glad I got that other question done because I got stuck on that for hours and finally realized the solution that would work, that would be reasonable. Ugly number is a positive integer that is divisible by a, b, or c, given 4 integers n, a, b, c, and c. N, a, b, and c return the nth ugly number. Oh, you know what? I forgot about that other question, that multi-threading question. I probably should have used scoped locking or something. Scoped locks, I think, is what I probably should have used with my mutexes, but I didn't really think that. I forgot about that part, but that's okay. That's fine. Anyway, so okay. Given 4 integers, return the nth ugly number. An ugly number is a positive integer that is divisible by a, b, or c. Okay, it's divisible by 1, 2, or one of those three. The nth ugly number. A is 2, B is 3, C is 3, N equals 3. The ugly numbers are 2, 3, 4, 5, 6, 8, 9, 10. The third is 4. 1, 2, 3, 4. Or excuse me, 1, 2, 3. Oh, I see. That's an interesting question. Ugly numbers are 2, 3, 4, 6, 8, 9, 10, 12, 4, 6. So A times B times C is less than or equal to 10 to the 18th, so it could fit in a long. And it's guaranteed the result's going to be between 1 and 2 billion. Is a very low acceptance rate. Jeez. Hold on, how many are we doing here? 2 minutes? Okay. And the value is going to be between 1 and a billion. These numbers A, B, and C are not necessarily sorted, so I probably want to sort those. Sort those numbers. Okay, this is an interesting question. What this is referring to is actually this is a good question. An interesting question. It requires some mathematics. I think you can solve this in logarithmic time. I think that's what it's going to have to be. It can't be done in linear time, so it's got to be something sublinear and most likely logarithmic. The interesting part is these three numbers may or may not be prime numbers. By the way, they happen to be prime in the examples, but these are not necessarily prime numbers, so we may need to perform some prime factorization first. But maybe not really, actually. It doesn't matter, I think, the way this is set up. And basically, each number, there's a certain number of multiples before the next number is meaningful. This is, oh, okay. Excuse me, never mind. Not multiples. I was thinking exponents, but actually it's actually multiples. Yeah, a certain number of multiples. Oh, okay. Well, that's very interesting. Counting the number of multiples, you can count the number of multiples of these three numbers using the inclusion-exclusion principle. And the nth number is basically just going to be a number such that there are n minus 1 numbers that are smaller. That number is a multiple of these things, and there are n minus 1 of those numbers that are smaller. I want to say a kind of binary search can be used here. How many multiples are smaller than a particular number is probably the way to go. And then what's the nearest number that's a multiple of these other numbers? So multiple of these other numbers, and it's excuse me, it's a multiple of these other numbers, and it's oh boy. Oh man. It's a multiple of these other numbers, and it has, X number of numbers that are multiples that are smaller. Because then I can use a binary search, then to find this value. Problem is figuring out what's the next number that shows up in these multiples. That's a good question. That is a good question. Is there an efficient way to figure that out? The largest number. Oh, you ready? Okay, ready for this? Excalidraw. Let's go. Let's go. I like the dark mode. Okay. So given some value x, I want to know number of multiples such that we'll call it y, such that y is less than x, or y equals x. Number of multiples y such that let's do it this way. Number of multiples k sub I, so that k sub I is less than x. For all I one to z, and z is less than x. I don't know, it's confusing. It's A and B such that for a given A, there exists B multiples K sub I such that for all I element of 1 to B, comma, K sub I is less than or equal to A. Something like this. Something like this. For a given A, for a given A, AB is such that for a given A for some A, AB is such that for some A there exists B multiples K sub I such that for all I element 1 to be inclusive, K sub I is less than or equal to A. Okay. If K sub B is not equal to A, then find K sub B efficiently. Efficiently from A. Okay. Yeah, that's the tricky part. Sublinear should be. Now, if A is a multiple, excuse me. So this is what I would be writing down on my. This is what I'd be writing down on my piece of paper, which normally you would not be able to see this. I don't know if this is that easy to do, because I'm fairly certain I can binary search. I could binary search on A, and I can calculate B in constant time using the inclusion-exclusion principle, because this is, I think I can use the inclusion-exclusion. I think it's not that hard to prove what the multiples are that are less than a particular value. The problem is which multiple is going to be closest. Well, there's only so many options actually. This can be done in constant time. Given the problem statement. Given the problem statement. This can be done constant time. Yes, so if we go back to the problem statement, the reason this can be done in constant time is because each of these multiples fall into different groups, different categories. So there's the multiples of strictly 2, strictly 3, strictly 4, and then combined 2 and 3, combined 3 and 4, combined 2 and 4. then combine 2, 3, and 4, right? All the multiples fall into those different groups, sort of the Venn diagram of A, B, and C. We have A alone, B alone, C alone, A and B, B and C, A and C, and A, B, and C together. And then obviously there's the empty set as well, but which this corresponds to the power set of those sets A, B, and C. Combinations, right? And 3 choose 1, 3 choose 2, 3 choose 3, and then 3 choose 0 would be the empty set. But obviously we're not considering the empty set at all here. So anyway, I can just find each of those multiples, what the largest value of those multiples is. That's less than the value that I'm binary searching on. And that's the answer to what we were just describing. So yeah. Okay, so binary search it is. So we can do int, we'll say alpha is 1, beta is 1 billion, and result's going to be 2 billion. Okay, 2 billion. Let's do, yeah, that's fine, actually, that's fine. While loop, and we'll say best. Actually, best is not quite what we want. Well, yeah, if it's equal, alpha is less than beta. Come back to this in a moment. Which if it should be less than or equal or whatever it is. So if mid is going to be beta plus, so beta is going to be the larger of the two, alpha is the smaller of the two. Beta minus alpha, bit shift to the right 1. So create this midpoint. Now we calculate a number, and there are a few options. So let's just call this total or smaller, right? So if smaller is less than n, if smaller is greater than n, and now if smaller is equal to n, there's a little more work that needs to be done here. So this is how many multiples. We'll just say multiples. If the multiples are less than n, that means I need to go to the right, which means I've got to set alpha to mid plus 1. If multiples is larger than n, that means there are too many multiples, so I've got to take beta down to mid minus 1. And we keep going until we find the number of multiples being exactly equal to n. Then once I've found that value, so two things, I have to calculate how many multiples there are that are less than or equal to this midpoint. And the second thing I need to calculate is, once I figured that out, once I figured out a number such that the number of multiples is less than or equal, then I've got to find the largest of those multiples, which is not that hard. It's just going to be from these 3 different sets of multiples. So each set of multiples, as I mentioned, the inclusion-exclusion principle, going back here, we've got A union B, oops, A union B union C, size by inclusion exclusion principle is going to be the sum of A, B, and C minus the intersections, which there should be 3 of them, A, B, AC, and BC. And then finally add the intersection of A, B, and C. And I don't know. I'm not sure exactly how to calculate these. So in the example they gave, let's do 2, 3, and 5 is relatively easy because they're all prime numbers. So it's relatively straightforward to calculate these values. I think it's going to be, suppose we'll use X, Y, and Z. Then size of A, and we'll say T is 100, right? A is going to be 100 divided by 2. It's going to be the size of 2 times 1, right? Two times X, such that 2 times X is less than or equal to 100, which means that X is less than or equal to 100 over 2, which is 50, which gives me size of 2 to 50 inclusive, which is 50 minus 2 plus 1, 49. Okay, size of B is a similar thing, 3 to 3x being less than or equal to 100, less than or equal to 100 over 3, which X is then less than or equal to 33, which is the floor of 100 divided by 3, right? So 33 times 3, which then gives me which actually should give me 1 to 50, excuse me. There shouldn't be 2, there should be 1. Which is 50. So I think each of these are just, this is the same thing, size from 1 to 33, which is 33. Which I think these are just going to be, it's just going to be the floor of T over, we'll call it like M sub I. And I think C is just the multiples of X times Y. Or not C, A and B is then T over 2 times 3. Just T over 6. Which is going to be 16 in this case. Where T is 100. Right, 16 times 6 is 96, and 7 times 16 is over 100. Hopefully you can see this too. Read what's happening here. So my question is, I think it's actually not that bad. I think I could just calculate these things, right? It's just gonna be we'll just call them set 1, set 2, set 3, 7 sets that we calculate. I think this is fine. So this is going to be mid divided by A. And this is integer division. It gives me the floor. Mid divided by C, B, C. S4 is A times B. Let's even do it this way. Mid divided by A times C. Mid divided by B times C. And then finally S7 is mid divided by A times B times C. Okay. And then multiples are going to be S1 plus S2 plus S3 minus S4 minus S5 minus S6 plus S7. Okay. And then we're looking for the largest of these values, which I'm going to say int vals of val 7, val 0. It's just going to be S1 times A S2 times B, S3 times C, S4 times A times B, S5 times A times C, 6 times B times C, and S7 times A times B times C. And I just want the largest of those values. Okay. Something along these lines, I think is what we're after. Wrong answer. Oof. Okay. -1. No. No. All right. So 2, 3, and 5. Excuse me. I don't know. Oh, I got it now. Okay. I got 4 and I should have gotten 6. 2, 3, and 4. Okay. So I was saying before, I think this is a little bit easier if you have, if the numbers are prime, this works nicely, but if they're not prime, it gets a little more complicated. And indeed it does. So here I'm looking for n is 4, right? 1, 2, 3, 4 should be 6, but I got 4. What are the numbers that I came up with here? Multiples, and mid. Put it. Get a new line character here. What happens here? That test case. It's close, but not quite right. Not quite right. Okay. So mid is 5, expected 6. Multiples are 4. It's 4. Okay. So 5 has 4 multiples that are smaller. 1, 2, 3. 5 should only have 3. How did I get 6? Okay. Or how did I get 4? Somehow I got 4. Okay. Let's see. What are these values? It's 3. It's 4. It's a bit tedious, but this is okay. That's 5. 6. 6. And 7. Alright. Okay. So with 2, 3, and 4, I got 2 and 4, 3, 4. That's correct. S4, S5, and S6 were all zeros. Okay. Oh, but here's the thing. Oh. Because S3 is a multiple of S1, this intersection it's actually not. Okay. These values are not A times B. I think it's the LCM of A and B. LCM times GCD is equal to A times B. LCM of AB and GCD of AB, multiply them, you get A times B. If you divide A times B by the GCD, you get the LCM. Yeah, that's what it is. That's what it is. That's the issue. I didn't realize. I was gonna say it's a little more complicated than what I was letting on. I kind of messed that up. So, one. That's what I need. Yeah, this is kind of subtle. Easy mistake to make. Yes, that's what I need. Let's see, one. Actually, I should do it this way. 4, 5, 6, and 7. That's what I was missing. Right. It's not that much easier. It's just a little bit. Okay. That's fine. So this should be correct now, I think. Just needed to consider the LCM. Yeah. Successfully reconnected. Okay. I don't have an LCM function. No. No. Maybe it's this one. Oh, okay, never mind. No. I mean, this works too. Really should be able to do more than one. Yeah, there we go. That's right. Really should be able to do more than one. What do they call that? Argument. Like you should be able to do a variable number of arguments to an LCM or GCD, but whatever, it's fine. Okay. So I think that's it. Yeah, I think that's it. Let me see how we doing. Live stream still going. Yeah. Some drop frames before. It's kind of long. Maybe I just go for it. I don't know. I'm tempted to just go for it. Let's do some more test cases. Let's do like 1,000, 1, 20, 50. Yeah. Let's do like 5, 10,000, 1, 2, 3. All right, let's try a bunch of test cases like this. All right, I'm gonna go for it. I'm going to go for it. Could be wrong. Could be something subtle that I missed. Oh, ouch. Very close. Oof. No. What happened? Oh no. Oh no. Shoot. I did something wrong. Dang. Dang. What did I do? 7884? Hmm. Hmm. What happened? Hmm. I don't know what to say. How could this happen? Could this be? How could it be? What happened? I don't know. I don't know what's wrong. Oh, look at that. Oh, it's in negative numbers. Oh. Well, that's not supposed to happen. What happened there? Negative numbers? What the heck? What? Huh? What is going on there? What? Oh. It's an overflow error. Oh, I didn't even think about that. Oh no. Oh, that's subtle. I see. My goodness. My goodness. That is very subtle. That's very subtle. That was the problem. Wait, what? -1. What's the LCM of B and C? What is going on? What is going on? What do you mean? I think I need to convert these to, I think B and C need to be converted to longs. A, B, and C. Can I do this? That might be it. There we go. Okay. Yeah, that's why. Gotta be kidding me. Yeah, it's annoying. Okay. Sucks. Yeah, it wasn't enough to... That's really annoying. I see why this has such a low acceptance rate. I see the problem. That sucks. That sucks. I didn't even think about that. That's so subtle. That's such a hard thing to catch. That these are, yeah, the LCM is going to be not going to fit in an integer. I didn't even think about that. Didn't even occur to me that that could be a problem. I was so excited just to get this part, just get this far. No. All right. Let's see. How did I do now? Now I got it. 2 milliseconds, kind of slow. How am I doing on time? Dang. Dang. It's rough, dude. It's rough. I'll submit it like 7 times. Disappointing that I got that wrong. There you go, 100%. Not bad. Not bad. Not bad. 1, 2, 3, 4, 5, 6. I'll submit it a few more times. Gee, it's a little bit slow because of the conversions between integers and longs. But yeah, the basic idea is there. Just use the LCM to set things right. So yeah, it's kind of a longer solution, a longer time to come up with this. I really should have been able to come up with this faster, I think. So yeah, if you like this, like that, if you like this stream, give the video a like and subscribe for more. I think with that, I will go ahead and stop there. So yeah, thank you for watching. I don't know if I'm going to do another one. I might want to take a break for a while. That was kind of rough. That wasn't too bad, but it was I definitely should have been able to figure this out faster. Figure it out faster and also not get it wrong. 2. Should have thought about the integer overflow involved with an LCM calculation or multiplication calculation, which is like the same thing as an LCM. Yeah. All right. One more submission, I think. Yeah. Take care. Take care. That's good. That's good. Not bad. Not bad. All right. Yeah. Have a good night. Have a good day. Or just, yeah, I'll just say goodbye, I guess. Just say take care.